Right, so today we're going to talk about something called partial fraction decomposition. And what this allows us to do is it lets us to go backwards from when we were adding and subtracting rational expressions. So I have two expressions right here. Now we're not actually going to go and add them, but I'm going to tell you what the answer would be. So if we add the first two, it would be x plus 7 over x minus 3 times x plus 2. And the second one would be negative 5x minus 6 over x plus 2 squared. So what partial fraction decomposition allows us to do, if it allows us to go backwards. So if I gave you x plus 7 over x minus 3, x plus 2, what two fractions did we add to get that? Well, that was 2 over x minus 3 minus 1 over x plus 2. So we're going backwards. What fractions did I add up to get negative 5x minus 6 over x plus 2 squared? Well, I added these two fractions in order to get that. So again, partial fraction decomposition is when we take a rational function and write it as a sum of multiple rational functions, essentially going backwards from the addition or subtraction. Now, something to note, and you're only really going to see this in calculus, but if a rational function is improper, which means the degree in the numerator is greater than the degree of the denominator, okay, like when we were graphing rational functions, that would be, well, we had to divide and get an oblique asymptote. But if we had that situation here, where the degree in the numerator is bigger than the degree in the denominator, we will do long division, and then we do partial fraction decomposition for the remainder only. But that's only done in Calc 2. So that's why we're not really going to see it today with this stuff, because not a lot of us are going on to Calc 2. But if you do, then that is something you might experience, and I'm sure you'll learn it at that point. So our first step after making sure we can do partial fraction decomposition is to factor the denominator completely. Now, for each linear factor, remember linear factor, that's like x plus 2. It's x to the first power plus or minus a number. We write as a sum of a constant over the factors in the form of a, so some number over px plus q. And all this stuff will make more sense when we go through an example. Now, if we have a quadratic factor, we write as a sum of a constant over the factors in the form bx plus c over ax squared plus bx plus c. So you'll notice that the degree on the bottom is bigger than the degree on the top for both of those. Then we're going to multiply each side by the LCD, or the least common denominator, to get rid of all the fractions, which that should feel familiar from solving rational equations using the LCD method, where we multiplied both sides by the LCD to get rid of all our fractions. It's the same idea here. We're going to do that to get rid of all our fractions. Then after that, we're going to either set up a system of equations where the coefficients of each term are set equal to each other, or use convenient values for x. So set up a system of equations or use convenient values for x and solve for a, b, and c. Most of the time that will work, but there's going to be times where maybe we have to set up a system. So the first example we have here is negative 5x minus 3 over x squared minus 9. Now, it's an improper fraction, so or it's not an improper fraction, so we don't need to do long division first. Now, I have some of the steps written out here because this is a longer process. So first, we're going to factor x squared minus 9 into x minus 3 times x plus 3. Now, we're going to rewrite this as a constant over each linear factor. So we have negative 5x minus 3 over x minus 3 times x plus 3. So we're going to do a constant over x minus 3 and a constant over x plus 3. And what we're trying to figure out is what these a and b values are. But we're setting this up so that these things are equal to each other. Okay, so I'm just going to write that down here. Negative 5x minus 3 over x minus 3 times x plus 3. That equals some constant over x minus 3 plus some constant over x plus 3. Because again, to add these two fractions on the right here, to add these two fractions, we would need a common denominator. So the LCD is going to be the x minus 3 times x plus 3. So we're going to multiply all three fractions by this. And we're going to see a shortcut develop, but I'm not going to do it right now. So we're going to do negative 5x minus 3 times x minus 3 times x plus 3 all over x minus 3 times x plus 3 equals a times x minus 3 times x plus 3 over x minus 3 plus b times x minus 3 times x plus 3 over x plus 3. Okay, now we can cross off factors from the numerator and denominator. So when we do that, the x minus 3 and x plus 3 cancel for the left side. So we get negative 5x minus 3 equals, the x minus 3's cancel off for a, so we have a times x plus 3. And then for the b1, we have the x plus 3's cancel, so b times x minus 3. Now, at this point, you may be tempted to distribute the a and b, but we're not going to do that because we need to figure out what a and b are. If we substitute in, and again, we have an equal sign here, so these two things are equal for all values of x. If I substitute x equals negative 3, that's going to make this part here 0. So I'm going to write this over here where we have room. If x, let's get rid of this. If x is equal to negative 3, okay, if x is equal to negative 3, we have negative 5 times negative 3 minus 3 equals a times negative 3 plus 3 plus b times negative 3 minus 3. Well, this part right here is 0, because negative 3 plus 3 is 0. 0 times a is 0. So on the left side, we get positive 15 minus 3 equals b times negative 3 minus 3 is negative 6. 15 minus 3 is 12. So 12 equals negative 6b. And then we divide both sides by negative 6. B is equal to negative 2. Now if I do the same thing for x equals positive 3, okay, that's going to be negative 5 times positive 3 minus 3 equals a times 3 plus 3 plus b times negative 3 plus 3. Whoops. It wasn't the order. 3 minus 3. So again, right here, whoops, I want to do that. This is equal to 0. So we have 15 minus negative 15 minus 3, it's negative 18, equals a. 3 plus 3 is 6, so we have 6 times a. And again, that is 0. And then we divide both sides by 6. A is equal to negative 3. Now, something to point out, what if back here I did x plus 3 right here and x minus 3 right there. Does that make a difference? No, that's not going to make a difference, because whatever we set up, no matter what we did A or B, whatever we have on top of the x minus 3 factor is going to be negative 3. Whether you called it A or B, it doesn't matter. Whatever you have above the x plus 3 factor is going to be negative 2, whether you called it A or B. So now we're going to substitute that back in. So it's going to be negative 3 over x minus 3 plus negative 2 over x plus 3. I just substituted in my A and B values up here. So these two fractions, and if you want, you can check it. If you add these two fractions, getting common denominators, you will get what we started with, negative 5x minus 3 over x squared minus 9. Now, example number 2, all right, let's start by factoring. So it's going to be 2 over x minus 3 times x plus 2. And this is going to equal a over x minus 3 plus b over x plus 2. Now we're going to multiply everything by the LCD, which is generally going to be the denominator of the original fraction. So x minus 3 times x plus 2. Now I'm going to do a shortcut in this problem. Notice how up here what canceled, our denominator is always canceled out. So now instead of rewriting everything, I know when I distribute the x minus 3 and x plus 2 to this first fraction here, it's going to cancel out with everything. We're going to be left with 2. Then when I distribute the x minus 3 and x plus 2 to the A1, the x minus 3 and the x minus 3 are going to cancel, and I'm going to be left with a times x plus 2. Plus, when I now distribute this to the b fraction, the x plus 2's will cancel, and we're going to be left with b times x minus 3. So that just saved all the canceling out. What we did right here, we saved that step. Now we can go to our convenient values of x. So x equals negative 2, we'll make that 0. So let's do x equals negative 2. So 2 equals a times negative 2 plus 2 plus b times negative 2 minus 3. Again, this is going to be 0. So we're going to have 2 equals negative 2 minus 3 is negative 5. So negative 5b. And we divide both sides by negative 5. B is going to be negative 2 fifths. Now we have to do x equals 3 because that makes this factor 0. So 2 is equal to a times 3 plus 2 plus b times 3 minus 3. This is 0. So now we have 2 equals 3 plus 2 is 5, so 5a. A is going to be 2 over 5. And that's because we divide both sides. If we divide both sides by 5 here, and the 5's cancel, we get 2 fifths. So now when we go back to our original and substitute these values in, it's going to give us an issue because we're going to have a fraction within a fraction. So the number on top of a is 2 fifths. So we have 2 fifths over x minus 3 plus, well, our b value was negative 2 fifths over x plus 2. Now we can't have a fraction in the numerator, a fraction within a fraction. So what we're going to do is we're actually going to factor out a 1 over 5, or a 1/5. So if I factor out a 1/5, that will leave us with 2 over x minus 3 plus negative 2 over x plus 2. You don't necessarily need those parentheses in the denominator. Now, if you wanted to double check, if I distribute this 1/5 back in, 1/5 times 2 is 2 over 5. 1/5 times negative 2 is negative 2/5. So that's a way you could check to see that you factored out the GCF correctly. So we are going to be having a few problems where we're factoring out a fraction. So I wanted to make sure you knew what that looked like.
So if we have repeated linear factors like an x minus 2 quantity squared, then we have to have a separate fraction for each power. So an x minus 2 and then an x minus 2 squared will need to be present. We're still going to do all the same steps that we've been doing, but with these, picking a convenient value for x isn't always possible. So in example 3, we have the degree in the numerator smaller than the denominator, so we do not have to use long division. So I'm going to factor that denominator first, and then that would factor into x squared plus, x times x plus 1 times x plus 1, but then we're going to combine that to x plus 1 squared. So what that means is that when we do this, when we set up these fractions, okay, we're going to have the original 5x squared plus 20x plus 6 over our factored form. It's going to have one fraction, a over x, plus b over x plus 1, but because I have x plus 1 squared, I must also have c over x plus 1 squared. Because the least common denominator between all three of those fractions is x times x plus 1 squared. So we have to have that extra term. Now, if we had x times x plus 1 to the third power, then we'd have a fourth fraction plus d over x plus 1 to the third power. But we're going to follow the same steps. Multiply everything by the least common denominator. This does get a little bit hectic, because now what happens, the left side still will be 5x squared plus 20x plus 6, but on the other side, when I distribute this, okay, when I distribute this to the a, the x's get canceled, so it's going to be a times x plus 1 squared plus, when we distribute it to the b, just one of the x plus 1 squareds will get canceled. So it's going to be b times x plus 1. And then when we distribute it to the c term, the x plus 1 squareds will be canceled, so it's going to be c times x. So, like I said, finding a convenient value for x in this one might be a little bit tricky. You may say, well, what about -1? Well, if you do -1, that will only give us the c term. And they say, okay, what about x equals 0? Okay, yeah, you could do x equals 0, but then we wouldn't be able to figure out what b is, because if we plug in -1, this part would be 0, which gets rid of our b. And if we plug in x equals 0, that part will be 0, so when we multiply that, it gets rid of our b. So using the convenient values is not going to be helpful in finding all of our terms. We'll only be able to find a and c, and we won't be able to find b. So what we need to do is multiply this nasty expression out. So we have a, x plus 1 squared is x squared plus 2x plus 1 plus bx squared plus bx. I multiplied like that, plus cx. Now I'm going to distribute that a. So 5x squared plus 2x, 20x plus 6 equals ax squared plus 2ax plus 1a plus bx squared plus bx plus cx. So what we need to do then is to figure out and match up our terms. So what I mean by that is that we have 5x squared. That means if we add ax squared and bx squared, that needs to equal 5x squared, meaning a plus b must equal 5. Then for 20x, we have 2ax and bx. So when I combine those, and cx, when I combine those three things, I must get 20. And then 6 and a, well, that one is easy. That one tells us right then and there that a has to be 6. So we have the three terms we're trying to figure out. We're trying to figure out the x squared term. And for the x squared term, we said 5x squared equals ax squared plus bx squared, meaning 5 has to equal a plus b. Well, we don't know what a or b are right now. Then in red, we had the x term. So 20x equals 2ax plus bx plus cx. So that means 20 must equal 2a plus b plus c. And then we have the constant term. Where 6 has to equal a. Well, that tells us exactly that a is going to be 6. All right, now we're going to be treating this kind of like a puzzle. Like we may not be able to find x squared first, or maybe we won't be able to, we weren't given the constant term like we were here. So you have to look at this as a whole and see what do we know and what can I use then to figure out something else. Well, now that we know that a is equal to 6, we can substitute that in right here. So 5 equals 6 plus b. Negative 1 is equal to b. So b equals negative 1. And then we can go to the red and say, okay, 20 equals 2 times a, which is 6, plus b, which is negative 1, plus c. So 20 equals 11 plus c. Subtract 11 from both sides. C is equal to 9. So now I have my ABCs that I can substitute back into this up here in black. So our final answer is going to be 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared. So this process can get rather confusing. We just have to make sure we are very organized with our work so we can see where things line up. All right, last one. We have 2x squared minus 9x plus 11 over 3 times x minus 2 to the third power. Now that 3, what we're going to do is we're going to factor out that 3 in the denominator by factoring out a 1/3. So when we factor out a 1/3, that gives us 2x squared minus 9x plus 11 over x minus 2 to the third power. Now, lucky for us, the denominator is already in factored form. So then it's going to be 2x squared minus 9x plus 11 over x minus 2 to the third. equals, we have a over x minus 2. And like I was saying earlier, we have to have a fraction for each power of the denominator. So we're going to have to go all the way up to c in order to get x minus 2 to the third power. Right, then we're going to multiply everything. Multiply everything by x minus 2 to the third. So the left side is going to be 2x squared minus 9x plus 11. The a term is going to be a times x minus 2 squared, because the 1 in the denominator only takes care of one of the 3 in the numerator, plus b times x minus 2 to the first power, because we have 2 in the denominator, 3 in the numerator, and then plus c, because we have the same amount in the numerator and denominator. So then we will simplify. So we have 2x squared minus 9x plus 11 equals, well, x minus 2 squared, if we use our shortcut, simplifies out or FOILs out to that, x squared minus 4x plus 4, plus bx minus 2b plus c. All right, so then 2x squared minus 9x plus 11 equals, we have ax squared minus 4ax plus 4a plus bx minus 2b plus c. Okay, so then we're going to start matching things up. So our x squared term, we have 2x squared equals ax squared. Do we have any other x squareds? No, we don't. So we can actually just solve that and say, oh, a is equal to 2. All right, now let's go over and look for the x term. So negative 9x is equal to negative 4ax plus bx. So yeah, we could solve that right now because we know what a is, but I want to write out our constant term. So then our constant, we have 11 is equal to 4a minus 2b plus c. Now in this one, we won't be able to figure out c until we know a and b, whereas the one above, we were able to figure out c right away. So negative 9x equals negative 4 times 2x plus bx. So we can get rid of the x's, so negative 9 equals negative 8 plus b. Add 8 to both sides, negative 1 is equal to b. Then over here, with our constant, 11 equals 4 times 2 minus 2 times negative 1 plus c. So 11 equals 8 plus 2 plus c. 11 equals 10 plus c. So c is equal to 1. So we have our a, b, and c's now. And at the very beginning of the problem, we factored out that 1/3. So our final answer needs to have that 1/3 factored out. And we have a value, which was 2. So 2 over x minus 2 plus b, our b value was -1, -1 over x minus 2 squared, plus our c value, which was +1 over x minus 2 to the third power. And that would be our final answer. So the fraction decomposition does get a little bit easier the more you do it, and the better you are at matching up your like terms and creating this little table here and treating that as a puzzle. So thanks for watching the video. Make sure to like it and subscribe.